Now, your linear algebra professor will probably tell you that the span of a vector, or the span of a set of vectors, is all possible linear combinations of that set of vectors. But in my experience, that never really gave me a good visualization of what that really means. So, my goal for this video is to show you what that visualization is, and hopefully you can understand it a bit better. Alright, so let's take a look at this purple vector here. Alright, so if there's only one vector in our spanning set, we can't add it to any other vectors because it's the only one, right? So all we can do is scale it by some multiple, which can be positive, it can be negative, it can be greater than 1, it can be less than 1, it can be anything. So let's multiply our purple vector by -1. If we do that, we'll get something that looks like this, the opposite direction, right? Or if we multiply it by -1.5, we'll get something that looks like this. Or if we multiply it by 3, we'll get something that looks like that, right? And we can keep going to get every single point along this infinite line. So the span of that vector is an infinite line. Okay, but it's very important that you know that it's in the direction of that vector. You can't tilt the line in any way. It has to be in that direction of the vector. But now, if we have two vectors in our spanning set, that's what our green vector is here for. We can now leave that line. Alright, we can now leave our purple line and go venture into the green domain. Alright, and that's not a special linear algebra term, I just came up with it. Alright, so we can now venture off of our purple line into a two-dimensional plane. Alright, so we can take steps, since our purple vector is still in our set, we can take steps along the purple vector. But now that we also have the green vector, we can take steps off of that line in the green direction. But what if we multiply the green vector by a negative scalar? We can then go in the opposite direction too. So now we have kind of our own little coordinate system going, where we can take steps along both of these axes to get to anywhere in this two-dimensional plane. Alright, so if I want to get up here, say I wanted to get to this point, we can take a step in this direction along the purple vector. See, that's 3 times the purple vector, and then we go up maybe another 3 times the green vector. I don't know what the exact measurement of that is, but it's something similar. Alright, so the point is we now can span the entire two-dimensional plane here. Alright, and maybe we have 3 vectors and one sticking out of the page. Alright, and if we multiply that by a positive scalar, we can get points coming out of the page. If we multiply it by a negative scalar, we can get points going into the page. So now we can span an infinite 3-dimensional space. Right, but what if we now have 2 vectors in our set that lie along the same line? Alright, so if we take steps in the direction of the purple vector, we can go this way and we can go this way, right? If we take steps in the direction of the green vector, we can go this way, right? And we can go this way. So we can't get off of that line. Right, so it's two different vectors in our set, but it's only given us one line. So unlike the first example, these 2 vectors can't span an infinite two-dimensional plane. They can only span this one line. So that's the whole point of vector span and linear independence and dependence, which you'll learn about later on. And the importance of this comes later when you're going to talk about finding the basis of a column space, basis of a null space, basis of any type of vector space or subspace. So this is something that you'll want to know, is something that you'll use a lot later on. Hopefully it's not too confusing for you, and good luck on your test tomorrow. I'm sure you'll do great.